Okay, so we're looking at an example of applying a chain rule when we have a trig function, and also when we have multiple steps. We're going to have more than 2 links here to our chain. So to do this, again, it really is important to realize what is the order that the function is going in. And we're going to deal with it in the opposite direction. So something that I use is I think, okay, if I were to plug a number in for x, what's the first thing I would do to that? I'd multiply by 5, right? Once I had that new number, what would I do with it? Would I take its sign or would I cube it? I'd take its sign, right? And then once I'd taken its sign and I have that value, then I would go ahead and cube it. Okay, so one thing to remember here, we don't write it this way, but this is equivalent to saying the sine of 5x cubed. Right? So when you see this cubed in here on the sine function, it means that after we evaluate the sine function, then we cube it. So it might be helpful if you kind of think of the order that we do things and you can work backwards. Right? So if you think maybe from inside to outside, so this would be our order of operations. The first thing we did was we did the 5 times x, correct? And then we take the sine function and then we cube it, right, would be how we would do that. If you were plugging a number in, you'd multiply it by 5, right, so 5 times whatever the input is, then you take its sign, then you'd cube it at the end. When we do the chain rule, we're doing backwards. First we're going to address the cube, then we're going to address the sign, then finally we're going to address the 5 times x. Okay, so that, I don't know, I guess we're going outside in, but you get the same idea there. So the first thing I want to address is if I'm cubing something, right? So if I'm cubing something, if I have u cubed, I know that its derivative would be 3u squared, correct? And in this case, u was the sine of 5x. So our first step here would be 3 times the sine squared of 5x. Right? So again, I got rid of the cube by putting it out front, and I dropped the power by 1. Again, this just means the sine of 5x being squared. The next part would be to deal with the sine function. What's the derivative of sine? Cosine. So it's going to be the cosine, whatever's inside, in this case the 5x will stay exactly the same. Right? We just do one piece at a time. The last thing we do is we take the derivative of 5x, which is just 5. Okay. Now, to be very careful, remember every sine function, every cosine function has to have an argument, right? This 5x has to be behind the sine squared. This 5x has to be behind the cosine. For the most part, you're never going to bring anything into a trig function or pull it out of a trig function, right? There's a few cases where that happens. We're not going to see those right now. We're going to leave them be. So to write this final answer, it would look best to say g of x equals 15 sine squared 5x times cosine 5x. Right? Whatever's after the sine is the argument of the sine. Whatever's after the cosine is the argument of the cosine. But notice that for the sine and the cosine function, you still have that 5x in there, right? You didn't change the argument of the function when you took the derivative of sine or when you got rid of the cube. You left the argument of the function, the inside of the sine function, the same. So here for our second example, we have f of x equals the quantity 1 plus the tangent x to the 3/2 power. Okay, so if we think about, if we were to plug a number in and think about what we would do first, the first thing we would do with our number is we would evaluate the tangent function, correct? So the first thing we do is the tangent function. Now the next thing we would do is add 1, but we're going to be able to take the derivative of 1 plus tangent x because 1's pretty straightforward. And then the next thing we do is we do add to 1. It's not going to be a huge deal. And then we're going to raise it to the 3/2 power. Okay, so that reminds us then that when we do the chain rule, first we deal with the 3/2 power, then we deal with add 1, which we could do that. We could do these two at the same time, right? Because as we look, we know that we could take the derivative of 1 plus tangent x. So you could just do it all at once. If not, you'd have to break it into a couple different lengths. So now, if it helps, if maybe you're like, boy, it looks really confusing with the 3/2 there, it might be worthwhile off to the side to say, well, I know u to the 3/2 is really what we're doing. I know its derivative would be 3/2 u to the 1/2, correct? And u was this whole 1 plus tangent x thing. So our first part, 3/2 out front, 1 plus the tangent of x to the 1/2 power, and now we'll take the derivative of what's inside. So the derivative of 1 plus tangent x, well, the derivative of 1 is just 0. Right? And remember, we're always multiplying, so 0, I'm not going to bother writing it. The derivative of the tangent of x is secant squared of x. Right? Now, if it would have been like a different argument in there, we would have kept that argument, but luckily it wasn't. So we have this. To write it, it's really not a terrible form the way it's written. Not horrible. I mean, there's other options, I guess. You could write 3 secant squared x square root of 1 plus tangent x over 2. Maybe you could see it like that. But again, I know that we're going to see all different forms when we do it. It just kind of depends if you can check your answers and make sure they're correct. Or I know delta math can be annoying sometimes. It'd be like, your answer is correct, but it's in the wrong form. And send you on a, wild goose chase. So, take this. So for our last example here, find the slope of the tangent line at x equals 2. We have f of x equals the square root of 1 plus the quantity x squared minus 1 cubed. So we have to figure out what order are things happening in, and we want to work from the outside in. I do know right away I'm not going to leave a square root there. I'm going to put everything inside of 1/2 power. So this is still f of x. This is not any part of the derivative, so I'm going to label it as such. Rewrite it as 1 plus the quantity x squared minus 1 cubed to the 1/2. So as we work on this, as we think about our inside to outside, so the first thing that we do is we would do the x squared minus 1 first, wouldn't we? Which we could put that all together because we know that we can take that derivative. So the first thing we do is x squared minus 1. The next thing we do is cube it, right? We cube and add 1. Because we know that if you just had like 1 plus u cubed, could we take the derivative of that? That would be fine, right? We don't have to do a whole new step. I'll show you. I think as we get there, it'll make a little more sense there. And then the next thing we do, the last thing we do is we do the 1/2 power of the whole thing. So again, just imagine if we're putting a number in for x. The first thing we evaluate is what's x squared minus 1. That gives us a number. Okay. Then we do 1 plus that number cubed. Gives us a number. Then we take that number, and then we take it to the 1/2 power. Okay, and the reason, again, that you can put some of these together, like the 1 plus we did here, or in the last one we had a 1 plus, is because we know that we can take the derivative of 1 plus all day, right? It's just going to be 0. Okay, so to do f prime of x, we're going to go backwards, right? So the first thing we deal with is the 1/2 power. We'll put a 1/2 out in front. And then we're going to get 1 plus x squared minus 1 cubed to the negative 1/2, right? Everything stayed the same except for that 1/2 power, right? 1/2 out front, negative 1/2 power. Now, the next thing we'll do is we'll look inside here, right? So to take that derivative, well, u would have to now take the place of x squared minus 1, correct? So here we're going to get the derivative of 1, which is 0, plus 3 x squared minus 1 squared. Again, I took the derivative of 1, I got 0, pulled the 3 out in front, dropped the power by 1. The last thing to do now is to take the derivative of what's inside here, which is x squared minus 1, which would just be 2x. So we had 3 links, correct? The first dealt with the 1/2 power, then we dealt with the derivative of the cube and add 1, and then we dealt with the derivative of x squared minus 1. So we need to clean this up a little. I guess we're going to plug a number in. So I guess we might not even really have to clean it up because we're going to put 2 in, aren't we? So let's just see what we get here. So we get f prime of 2. Well, here, let's clean it up anyways. I think that'll be worthwhile. So we get 1/2, 1 plus x squared minus 1 cubed to the negative 1/2 times 3 times x squared minus 1 squared. Oh, I guess it was 2x times 1/2, so we'll just put a x out in front. Makes it look a little bit nicer there. So now at this point, are we okay up till now? Yes?
Why did you take the derivative of 2x?
Oh, I took the derivative of this, this was like the inner part. Our first inner part was the x squared minus 1. So when you take its derivative, you get 2x. And then its inner part is x, but if you take the derivative of x, it just gives you 1. So, great question, though. Great question is kind of when to stop, right? So let's see here. So f prime of 2 is going to be 2 for the x, and then 1 plus 2 squared minus 1 cubed to the negative 1/2. This looks a little challenging at this point, doesn't it? Times 3, and then 2 squared minus 1 squared. All right, so we get to simplify here a bit. Let's just leave this here as 2. So this is going to give us 4 minus 1, which is 3, right? And 3 cubed is 27. So 1 plus 27, I guess that's 28. To the negative 1/2 power. That doesn't seem very good. Wait, okay, 4 minus 3, okay. Yeah, it's just not a very pleasant number. Sorry, I was hoping for something nice that we could actually take the square root of, and it didn't happen. And then here we'll get 3 squared, which is 9 times 3 is 27. So we get this, and then I would just need to get a calculator. This is a little bit beyond what I can do. Now, I mean, I guess if we wanted to make it exact, you could get 54 over the square root of 28, and then you could write 54, and this would be radical 4 times radical 7, if we had to get an exact answer. 54 halves, and that would be over 2, radical 7, not loving this. That would give us 27 over radical 7. And then if we rationalized it, we would get 27 radical 7 over 7. And I'm going to go actually check that on my calculator because I don't really trust my answer that much. But what I'm going to do is I'm going to graph this function on my calculator. And I'm going to go to the dy dx and type in 2 and see if it matches whatever that decimal expansion should be. So let's see if it works. All right, I did go ahead and check it. Again, I graphed this, dy dx, typed in 2, gave me this decimal, which then I typed this in, it gave me the same decimal. So it worked. I hoped it would have been nicer. Instead, it was a pretty awful number. But there you go.